Good morning, my name is Marcio and I will present your paper Predictive Actuator for IoT-based air conditioner unit. This work was developed by Henrique Tome at Western State University of Paraná. The energy spent on cooling system is growing fast year by year, and the cooling is considered the new electricity demand in the world. In data centers, the cooling is responsible for almost 50% of the total energy consumption. In this work, we aim to develop an actuator to decrease the air conditioner energy consumption in a small server room. The room has 3 servers and an air conditioner unit of 12,000 BTU. The room is monitored using external sensors to collect the external temperature and the humidity, and an internal sensor to collect the internal temperature, humidity, and also the current consumption of the air conditioner unit. All the collected data are sent to the ThinkSpeak platform. The sensors are built using the Arduino and the Node MCU platform. Temperature and the humidity are collected using the DHT sensor and the current using the SCT sensor. We also developed an actuator circuit in order to send the commands to the air conditioner unit using an infrared LED. This figure shows the overall flow of your work. The inside and outside sensors send the temperature and the humidity to the ThinkSpeak platform. A service developed in Python collects this data and selects a rule to configure the operation of the air conditioner unit. The select operation configuration, for instance, the temperature, or if we have to turn off the air conditioner unit, is written to the ThinkSpeak platform and read by the actuator sensor. The actuator sends the selected configuration to the air conditioner unit using infrared commands. 3 different actuators were evaluated in this work. The first one was the standard automatic mode of the air conditioner unit. This mode was monitored for 106 days. And we also have tested a simple rule actuator based on the time of day and the day of week, and a predictive rules actuator. This table presents the simple rules actuator. The rule is selected based on the day of the week and the time. For instance, on the weekend, we configure the air conditioner unit to work at 24 degrees because the server load is lower. At night, for instance, we have 2 options. If the internal temperature is lower than 24 degrees, the actuator turns off the air conditioner unit. And if the internal temperature rises, it turns on the air conditioner unit to 24 degrees. In the day, the air conditioner configuration is based on the internal and the external temperature. The predictive actuator uses a predictive model to estimate the current consumption of the air conditioner. To create the predictive model, we use the collected data of the air conditioner unit using the automatic mode. The training data uses the time of day, internal and external temperature, and the humidity, and also the collected current consumption of the AC unit. This table shows an example of a data tuple used in the training process. The time of day, the external temperature and the humidity are used as input, and the current in the next 10 minutes is the value to be predicted. In this work, we tested the Handel forest and the multi-layer perceptron models to estimate the current consumption, using 18% of the data for training, 10% for the test, and the 10% for validation. Data normalization was performed using the min-max scalar function. This table shows the results obtained using the multi-layer perceptron and the Handel forest models. The performance was evaluated using the coefficient of determination, and we have tested different configurations of the MLP and the Handel forest model. As one can see, the Handel forest obtained the best results. In this work, we also evaluated the Google AutoML cloud solution. The platform performs the data normalization and dataset selection. The AutoML was evaluated using 3 different window sizes, creating 3 different models to predict the energy consumption in the next 10 minutes, 20 minutes, and 30 minutes. Using the coefficient of determination as performance metric, the AutoML is the most accurate prediction model compared to the Handel forest and the multi-layer perceptron. So, in the Predictive Rules Actuator, we decided to use the AutoML predictor and change the rules to use the prediction of the energy consumption in order to configure the air conditioner unit. For instance, if the predictor returns a low demand of energy consumption, the actuator turns off the air conditioner. For the moderate power consumption, the actuator uses the prediction and also the internal temperature to decide the air conditioner configuration. And if the predictor returns a high demand of the energy consumption, the actuator sets the air conditioner unit to work at 24 degrees in order to induce fewer activations of the AC unit. In order to evaluate the 3 different actuators, we have to search periods with similar climatic characteristics, because the actuators were used in different periods and it's hard to reproduce the same conditions. So we select periods with the same time of day and the external temperature, a similar external temperature in the range of plus or minus 2 degrees Celsius. Comparing the automatic mode versus the simple rules actuator, we found 16 hours with similar external temperature, and the observed energy reduction was 17%. In this figure, we can see the behavior of the 2 actuators. The automatic mode turns on and off the air conditioner unit over the night in order to maintain the internal temperature. In blue, we can see the simple rule actuator. At midnight, it turns off the AC unit until the point A, when the internal temperature reaches 24 degrees, and the actuator turns on the AC unit again until the point B, when it's turned off the AC unit and the air conditioner unit becomes off through the night. Comparing the automatic mode versus the prediction rules actuators, we found 7 hours with similar external temperature. And comparing the energy consumption of the air conditioner unit the predictive actuator obtained a reduction of 37%. In the figure we can see also the air conditioner unit in automatic mode working during the night. In blue, one can see the behavior of the predictive rules actuator. At the point A, it detects a low demand in the energy and turns off the air conditioner unit. And 1 hour later, it detects this internal temperature rising and turns on the air conditioner unit. And this behavior is repeated along the night. When we compare the simple rule actuator versus the predictive rules actuator, we found 37 hours with similar external temperature. The energy reduction obtained using the predictive rules actuator was 15%. This figure shows the behavior of the two actuators. The red line represents the simple rules actuator. As one can see, the temperature of the room is rising during the day, and at point C, the actuators turn on the air conditioner unit. And the blue line represents the behavior of the predictive rule actuator. At point A, it turns on the air conditioner unit, and at point B, the predictor model estimates a low demand of the energy consumption and it turns off the air conditioner unit, and this state is maintained along the day. And it's an interesting scenario because it represents a rainy and cool day when the air conditioner unit is not necessary. Concluding this work, we compared the three different actuators, and we developed also a short-term predictive model in order to evaluate the energy consumption of the air conditioner unit in the next 30 minutes. The predictive actuator obtained an energy reduction of 37% compared to the standard automatic mode of the air conditioner unit. The future work includes the use of a local predictive actuator to avoid the access to cloud services, and also the fine-tuning in the predictive actuator to reduce the frequency of changes between the rules as observed in the results, and create and delete rules dynamically, and also use the local weather forecast in the prediction and in the rules to select the configuration of the air conditioner units. Thanks for your attention.